Roll-up space to more deeper level cryptography. Today we have Alberto Garroffolo, the head of ZK at Telos, who has been working on some revolutionary decentralized proof verification system for ZK snarks and how they enable to protect more user data at the application level. So welcome, Alberto. Really excited to have you here and to listen more about SNARKtor.
Thank you. Okay, hello everybody. I'm Alberto Garoffolo, head of ZK at Telos, and today I'm going to present to you Risclonky2, how to write scalable user data protecting application on blockchain, and leveraging both RISC Zero and SNARKtor. Okay, let's start from a very high-level consideration. Currently, just a small part of the real-world use cases are on blockchain, and all of us know because of lack of scalability and high fees, but there is another element that is less mentioned, is the lack of user data protection. And what do I mean here? On-chain, if I want to verify some statement on the data of the user, I require the user to share the data on-chain. But for many use cases, this is not acceptable. Let's imagine, I always do this example, we want to implement a car rental application. The car rental application will probably need to verify if you have a valid driving user license. And so currently, in the current architecture, I have to share my driving license information on-chain, and this is not acceptable. Very similarly, there is a growing need for compliance with government rules. And let's imagine I am a developer, I want to implement a casino game application, and I want to be sure that the user is over 18 to be compliant. And again, I will ask digital identity information to be shared on-chain, and again, this is not acceptable. And last but not least, interoperability. In the current very fragmented scenario where you have many layer 1, layer 2s, you need to have a secure and trustless way to have them communicating each other. Okay, I mean, very briefly here, the role of ZK. Everybody knows here about ZK rollups, how they enable trustless communication between layer 1 and layer 2. And for what regards instead user data protection, you remember previously we were speaking about having the chain verifying statements on user data. You can use ZK snarks in order to prove client-side some statements on your data and don't having to share your data on-chain. So in the car rental example application, this means that the user will share a proof that he has a valid driving license without having to share the driving license information. And this preserves his privacy. And very similarly, with the compliance thing, in the casino game application, you don't have to share your digital identity. You just share the proof that you're over 18. And for what regards the interoperability, succinctly proven chain allow trustless and secure communication between layer 2s, layer 1s, and so on. So now it's clear that we will have an ever-increasing volume of transactions that are relying on zero-knowledge proofs. And so the throughput of the chain is going to be heavily affected on the proof verification, on the efficiency of the proof verification. And even with the most efficient proving system in terms of proof verification, these can consume a substantial portion of the transaction budget or computational budget or the block budget. And the situation can be even worse if the use case or just left, let's say that you want to provide to the developer a way for writing the private logic in a developer-friendly way. You can then leverage a ZK VM, and then the verification efficiency of such proof is even worse. It's true that you can perform proof wrapping, but this is computationally expensive and can introduce additional latency that will make the use cases not viable anymore. So, and the last consideration, that proof verification can be a completely stateless task, but you are consuming stateful resources that are more scarce and more expensive. So let's now see how SNARKtor solved this issue in a decentralized and scalable way. So, very briefly, the main principle of the protocol. One unique proof that validates many proofs. We leverage recursive proof composition in order to create a proof that validates many proofs. And this is the proof that goes on chain. And the verification time of such proof is constant and independent from the number of the underlying proof. And here you can see in the scheme, instead of including the 4 proofs, we just include the aggregated proof that is the result of the recursive aggregation of the base proofs. And other 2 important principles are the decentralization and the scalability. I mean, and why it's important, the decentralization of the protocol. If just for compliance reason, you expect to have many transactions that are relying on zero-knowledge proofs, this means that the protocol will manage the aggregation of many proofs. And so many transactions will rely on the protocol. So if the system is not decentralized, this means that the system itself could become a censorship threat to the underlying network. So it's important that it is decentralized. And so we worked on a protocol that can inherit the same level or similar level of decentralization of the underlying chain. For what regards scalability, we modeled the protocol in order to have proof aggregation, so the merging proof process, but also the verification itself in primitive being parallelizable. So not requiring an actor to have to verify in primitive all the proofs. So that's another important aspect of the protocol. And obviously, being decentralized has an incentive scheme, the protocol, in order to lead to fair transaction fees, or better aggregation fees, and also fair reward for all the involved actors. Let's see a high-level scheme. Okay, very high level. The user submits his proof along with an aggregation request to the SNARKtor decentralized network. And then the aggregation protocol continuously aggregates the proof with recursive proof composition. And then periodically the protocol picks up one of the aggregated proof and submits it on chain. And the aggregated proof that was submitted on chain allows the user to indirectly prove that they had a valid proof. Here we can see another scheme from another perspective. So you can have several users that are, for example, proving that they have a valid driver license or other things, but even ZK rollups. You can see ZK rollups as users for the protocol. So you can aggregate all these proofs all together recursively, and you can end up with a unique proof on chain. And then the user and the rollups can submit the final transaction on chain referring to the aggregated proof. They don't have to send again their proof. They just send a proof reference. We called it SNARKtor receipt. And so now let's see who are the actors involved. Okay, the users, we already saw them, and the schedulers. The schedulers are entities that are coordinating the aggregation process. So they keep a proofs queue, and they pick up from this queue in order to create a schedule. And this schedule assigns the work of aggregating to provers. And the provers are the ones that are doing the actual work of aggregation. And once they produce the proof, they shared it. And then you have the submitters that are responsible for picking up the aggregated proof and submit it on chain. Okay, now let's see the flow. So the protocol operates in an environment where the time is divided in time slots of constant time duration. And users continuously submit their proofs, augmenting the scheduler's proofs queue, and every slot is assigned to a specific proof scheduler. At the beginning of each slot, the scheduler can pick up a set of proof and compose a schedule and assigning a proof tuple to each prover. And then the prover start merging the proof and share the proof with the other schedulers, and the resulting merged proofs are added to the proofs queue. The source proof are removed from the queue, and the newly incoming proofs from the users are added to the queue. So the next scheduler can create a new schedule aggregating again the new proofs. And this loop continues infinitely. And here we can see the previous schema with the addition of the submission flow, where let's say the submission, the submission environment is divided in submission epoch, and each submission epoch is assigned to a specific submitter. And typically, submission epoch can be bound, for example, to on-chain blocks. And then each assigned submitter has the responsibility of taking one aggregated proof, finalize it for submission, and submit it on-chain. And okay, this was a very high-level overview of the protocol, how it works. And one other thing that we have been working during this month is a POC that showcases how SNARKtor can enable scalable user data protecting application, like the car rental, for example. But we did it with two different examples. One that is leveraging RISC Zero ZK VM for the client-side proving, so a battleship example. And another one that is using directly Scalability2 for generating the battleship game proofs. And so we also built the aggregation protocol, the implementation of the protocol, in order to perform the recursive proof aggregation, and also the on-chain smart contracts and the SDK that is needed by the, in this case, the battleship game application on-chain to verify the proof reference. So in order to, when I say, verify the correctness of the claimed data. Okay, we can look in more details about the implementation, how it works. So in case of the aggregation protocol, we built it leveraging the Scalability2 recursive verifier, and we use it both for aggregating base proof and obviously the aggregated proof. So in order to have the fully recursive proof composition. And the final public input of the final aggregated proof is a commitment of the underlying base proof public inputs. So here we can see instead the on client side where we used, as I mentioned before, RISC Zero and Risclonky2. Okay, but let's go through it. So the user application is written with a Rust program. So let's say the battleship game logic is written in Rust. And the private data is also sent to the RISC Zero ZK VM in order to prove, let me say, the private statements. And so we end up with a RISC Zero receipt. But if you remember, our aggregation protocol is built using Scalability2, so we need to end up with a Scalability2 user proof. And so we wrote Risclonky2, let me say a RISC Zero Scalability2 wrapper in order to prove in circuit the validity of a RISC Zero receipt. And what we did in order to make it more efficient, considering that Scalability2 work on the Goldilocks field and RISC Zero is working on the baby bear field. So in order to reduce all the, let me say, the operation where was needed simulating the baby bear arithmetic, we introduced to the RISC Zero ZK VM the Poseidon over Goldilocks implementation. In such a way, for the whole the hash function, it was not necessary to simulate the arithmetic. And for what regards the arithmetic of the other operation arithmetic, we are using lookup arguments for, let me say, having better performances. And let me say, as a side note, the Risclonky2 proof wrapper supports receipts also with multiple segments. So you can see the Risclonky2 also a way for compressing RISC Zero proofs as well. Here you can see the overall scheme where you have the user application that are using RISC-Zero ZKVM. They generate the RISC-Zero receipt that is on Baby Bear, that we have the Risclonky2 wrapper that generate the Plonky2 user proof. And then the Plonky2 user proofs are aggregated recursively with the aggregation protocol that leverages the recursive composition of Plonky2. And so we end up with one unique proof. Okay, the next step will be to change the SNARKtor aggregation protocol implementation in order to not use any more Goldilocks, but switch to Baby Bear. And so in such a way, we will have the possibility to optimize the Risclonky2 wrapper in order to not have to simulate any arithmetic there. And so this will be very efficient and can become also a way for compressing RISC-Zero receipts. Okay, the other thing that we have been working is a prototype of RISC-Zero running on mobile. So in order to, now let's imagine the current application or any other application where you want to preserve user data. So let's imagine that you want to use a mobile native application to do that. So it's important that you can generate the proof on the mobile device as well. So we have been able to run the RISC-Zero ZKVM on Android, and in particular on a Samsung Galaxy S21, so pretty old phone. And the performances, without additional improvements, were very similar to average laptop. And so what we are going to do next is also to port Risclonky2 on mobile to perform also the other part, and so end up directly in the native application with the proof, the Plonky2 proof that we are going to use later in the aggregation process. And obviously, we are going to do the same on iOS. Okay, more in general on SNARKtor, what's next? We are going to implement the fully decentralized version of the protocol, and we are going to also hardware accelerate the prover that is used for proof aggregation, and this will make the performances of the proof aggregation much, much better. And finally, we are going also to integrate SNARKtor in our upcoming hardware accelerated ZK EVM layer 2. Okay, for what regards the POC, you can see it live at our booth. And for what regards the SNARKtor white paper, here's the QR code. If you want to see any more details about the incentive scheme or any other details about the protocol, you can have a look at the white paper. And that's it. Yeah, if you have any question, obviously, I'm here. Thank you.
Hi, thanks. Just a couple of questions. One is, you said the benchmark was comparable to desktop performance. Like, do you have like real numbers there? Like, I couldn't see it on the screen. Just in terms of like, you know, like if it's like a 1 million gate circuit or whatever, like how much time do you take on the phone?
I can show you. No, I cannot show you anymore. But
okay.
Okay, let's say that we tried the example loop and also the hello world example from RISC-Zero, and on an average laptop at that time it was taking around 15 seconds. And the same time was on mobile.
That's a small circuit, 15 seconds, you said?
Yeah,
okay.
It was around, yeah. But you can leverage also on the acceleration on the mobile.
Web GPU, I'm guessing.
Yes, exactly.
The other question is, the first stage of your proof with the ZKVM, is it ZK, is it the ZK snark, or is it just a snark?
Do you mean which?
Is it zero knowledge is what I want to know. Like the first client-side proving that you do with RISC-Zero, is it? Is
ZKVM proving? Yeah, we did two versions. We did two versions, for example, of the battleship example. One leveraging RISC-Zero and the whole, let me say, stack that I shown. And the other one was using Plonky2 directly in circuit, verifying the rules of the battleship game and generating the zero knowledge proof.
My guess is neither of them are zero. They're not private. Is my
They are
understanding?
private. Yeah.
Okay.
Why they should be private? Okay, sorry. Yeah. Why they should be private? Because the game should stay private. So you're keeping, you as a user, you are committing a board, and such board stays private, because otherwise you reveal to the other party where your ships are. And so for this reason, I mean, you need ZK in order to keep your board private, and then you're proving to the opponent that his shot was a hit, miss, or sunk. And so for this reason, you need ZK.
Okay, thanks.
You're welcome.
Okay, we're out of time for now.
Okay. Thank you.
Thank you.
Thank you, everybody.